Alright, so welcome to my science lab. I invited two guests, one from Brown University, Raf. He's a graduate student at Brown University, and I also invited supervisor from the Raf is a graduate student of physics at Brown University, which is an Ivy League. He gonna challenge Shubham Isaac on quantum mechanics, and I'm gonna set the premises. Okay, this is how he gonna try to challenge Shubham Isaac. So it doesn't matter, rest you are not visible. So okay, probably hopefully you are visible. So any conversation, be it quantum mechanics or be it GR, you can start with F equal ma. What does F equal ma tells you? It tells you.
Quantum mechanics distinctly going away from F equals ma.
Hold on. Okay, you're gonna attack. You're gonna challenge me at the end of now. Okay, what does that mean? If I give you the mass and I give you the acceleration, you can give me the force. Okay, great. So that's F equal ma. So the quantum mechanics is all about Schrodinger equation.
Well, yeah, I guess that's the most general way.
Okay. Let me finish. Alright. So what does H? H is like force, okay?
No.
Okay, alright, okay. I'm trying to make a connection.
There is no connection. Quantum mechanics is all about running away.
This is the F equal ma version of Schrodinger equation. Let me fast. Okay, this is how. This can be written as. Okay, this can be written as.
This is more related to linear algebra.
M d square x over d square t, and this can be.
You can even write d squared t correctly. It's dt squared.
Dt square, and this can be written as. This can be written as h square psi.
Step in.
Over.
Okay, there's a last one.
Hold on. H.
What?
Wait,
You can't do that.
No, that meant to write partial.
What's that?
D.
You can't
D
do
squared.
D square psi, and then d square x is equal to. Alright, so what I was.
Unfortunately, that's not the chemical.
No, that,
Okay.
that is the Hamiltonian for no potential. V is 0.
I'm trying to make it.
No, that's not. There's still a constant.
Minus h squared over 2m is just a constant. It's gone. Okay.
Actually, it's minus h bar squared.
Okay, you think you know
Okay,
more
H
about
is okay, alright, okay, H is fine. Okay, alright.
Okay, I'm sorry
now. You're not gonna argue with me, you're gonna argue with Brown. So,
But if I am gonna argue with you,
then I'll say,
because that's wrong.
this one doesn't have to follow Heisenberg. This one does.
Not the alternative.
Yeah.
So this one,
I know what the generalized uncertainty principle is.
You.
Yes.
okay. So I know you don't like Sir Isaac Newton for some reason.
Yeah. You hate him.
Oh my god.
Why? He is the most beautiful.
He was an arrogant
smartest.
parent. Did you just call Isaac Newton beautiful?
Yeah. Beautiful.
Okay.
Okay. All right. No, and I'm gonna challenge you. Okay. So.
Wait, okay, first of all, this is not similar to F equals ma at all. This is more similar to the eigenvalue equation.
He kicked me out. He kicked me out.
Let's hear out the conspiracy theories first.
Yeah, so this is more similar to something.
You can't resort to violence in a scientific
Am I
argument.
being violent? No. I'm using the language equivalent to violence, but that doesn't mean I'm getting violent. It looks more like the eigenvalue equation, right? Really, all you're doing here is trying to find the energy that happens to be the eigenvalue of the Hamiltonian operator. So
Okay.
this is all of quantum mechanics comes down to linear algebra.
Okay, I think that's a good argument. If it wasn't wrong. So let me explain. Let me explain my perspective.
Isaac, can you get closer because our camera is.
What do you mean perspective? This is math and science.
So look, I'm gonna write 3 words that I think you probably know. Heat, wave,
We're gonna write hell.
Can you allow me to join, Isaac?
Yeah.
No.
Okay.
And electron.
How do you spell that last one?
Okay, so let's see. You know the heat equation? Oh, and particle. Okay, actually, let's begin from bottom up. What is the...
I was supposed to solve the heat equation, but then I forgot about it.
Okay. What is the equation of... What is F equals ma?
Oh, you did not include heat equation in the book?
No, because it's not related to quantum mechanics. As far as
The
I'm-
conversation, yeah, it's a good analogy.
I'll show how.
I did the heat equation as part of ordinary differential equations.
Hmm.
Why would I need it for quantum mechanics?
Okay, let's take a look. What is F equals ma for...
I said, thank you.
Where do you put that?
Thank you. F equal mf. Thank
What have you done?
He.
No, what? Well, can you tell me what is F equals ma for a particle?
I don't know.
F equals ma.
Can I explain it?
Yeah. You wanna?
Isaac, can I? Okay. Sure.
Okay.
All right.
So, F equals...
I cannot see that color. Sorry.
Okay.
No,
Can you see maybe red?
I can. I'm not colorblind.
Okay. So, F equals ma. Another way we can write it is, don't get scared by a derivative. I know that.
Actually, in full, you would write it as...
dp dt. Yeah, okay.
Isaac, you have to stay there. Baby.
F you can also write as minus...
Everything comes down to potential.
Okay. Good. So this is another way to write F equals ma, right?
Yes.
Okay, you okay with this?
Die!
Okay. At the end, we're going to get to Schrodinger's equation. But do you know what the wave equation is?
Yes, I think
What's
so.
the wave equation?
No, not that color.
Oh. Here.
Remove that color from your hand.
Okay, I might be doing something stupid here, but the
Okay.
first thing that comes to mind
I agree.
is something else.
Let's see what mistake you're about to write. Let's joke. Let's see
The
what...
first thing that comes to my mind is something like this, but it's probably wrong.
That's a great attempt.
If it wasn't wrong.
Well, it's a great attempt. Let's write down what the real answer is. The wave equation is...
Why don't you write the simple one? H psi is equal to E psi.
oh, that will be here then.
Okay.
For the electron, yeah.
Well, because that's like the most general you can get. Sometimes you want to be more specific. Oh, shit.
This is the wave equation, right?
Yes.
And do you know the heat equation?
Wait, I thought it was d. Also, wouldn't those be partial derivatives?
Yeah, they're partial. But let's just keep things simple here.
Also, I
Yeah.
swear this was a single derivative, but I can't prove it.
Yeah, you can't. But look, you can think about it. See, the wave equation tells you what.
Isaac, you are outside the camera.
This is like acceleration, right? So the acceleration is proportional to what does the second derivative tell you?
Is that the Laplacian?
No, the second derivative tells you how curvy a string is. So for example, if you have a rope, right? Then
Oh,
the
this
parts
is
of the rope that are most curved will experience the greatest acceleration, right? That's all this is saying, right? Does that make sense so far? Okay, and finally, what is the heat equation?
I forgot. I used to know it, but then I quickly forgot.
Okay, that's okay.
I think you can derive it from first principles of what heat is supposed to look like, right?
Yeah,
Because heat is always supposed to flow from hot to cold,
yeah,
and never from cold to hot.
yeah.
So the heat flux, it all comes down to the heat flux. Oh yeah, there it is.
That's right. Yeah, you're right. Okay, now finally, what is the electron? What is the equation for an electron?
An electron doing what?
Whatever. Each side is E psi, a free particle. Okay, each side is E psi,
Hey,
right?
but free particles don't exist in quantum mechanics.
Yes, they do.
Wow.
It's called an ionized electron.
I thought I showed that their wave function is non-normalized.
That's why you have to get a superposition of the free particle wave function.
Interesting.
But what is H?
Oh yeah, that makes sense because
Uh-huh.
when you have that superposition,
Yeah.
now the combined wave function, basically one electron's wave function minus the other, and you use the minus sign because electrons are fermions. And of course, when you subtract one quantity that approaches infinity from another that approaches infinity, often it's going to converge to a finite value.
Yeah. Okay, so great. What is H for a free particle?
The Hamiltonian, isn't it just minus I H bar partial x squared or something like that?
Yeah,
Or minus h bar squared over 2n times the Laplacian?
you can just write it as p squared over 2m.
Isaac, can you get it closer?
Is E psi, right? Yeah. P squared over 2m is just another way to write kinetic energy.
Oh,
right?
I just realized
Yeah.
P is
Minus I H bar partial x. So
oh, so this is just squaring that. Oh, so that's minus h bar squared.
that's right. So
partial x squared.
I'm going to take out all the constants. I just want to keep it as simple as possible.
Raf, what I'm gonna ask you to sit down.
Oh.
Isaac can stand up.
Am I too short for sitting down?
No.
Time to go.
Good.
That's racist.
Good.
Okay, so I don't think anyone heard what I said.
No, it's not racist. It's loving someone.
No, it's not racist. It's
Okay,
ableist.
look.
I got the wrong guess.
So look, this is the Schrodinger equation, right?
Yes.
Compared to the other equations, what do you see?
They are mildly similar, but except, oh, wait a minute. One of them has a constant times d partial dt, partial phi partial t. One of them has partial squared phi partial t squared. One of them just has no derivative on the other side. But all of them have the Laplacian of phi.
Yeah, see the Schrodinger equation is very similar to the wave equation.
Yeah, so actually one way you can see it is basically, this is the first equation.
It will show people. I don't think people can see what you're writing.
This is the second equation.
Uh-huh.
And this is the third equation.
Yeah, that's right. And can you write Newton's equation? The F equals ma?
Oh, wait, no.
Yeah. Grad.
You want me to
And
actually
in fact, no, we're doing free potential, right? So let's,
oh, so that's a zero.
yeah, let's keep it simple.
So 0 is equal to the Laplacian.
Okay, now you can, and in fact,
Oh, wait, no,
Just
not the
in-
Laplacian, that's a position.
that's it for the, you need a time. So, let's make it all similar notation, so sine. Now,
Wow.
can you show everyone how these four equations are similar? Go.
Well, I mean, they just resemble each
No,
other.
I'm going to explain
Are the
after you write.
solutions really similar?
Okay, wait, first can you write it down, and then
Well, right what?
these four equations nicely.
Aren't they already?
Don't erase that one. Do it on the left side of the board.
This is the left side of the board.
Yeah.
Your left?
No, erase only left side of the board.
Write
it.
the
Yeah.
nice, write the simplified way to write these four.
Use the white color.
Go.
Okay.
And nobody knows what a Laplacian is, write it down. Okay, fine. Everyone knows.
Not everyone in the universe knows.
Yeah, so you should write it like in a way that everyone can understand.
Some fifth
Well,
grade,
if
some fifth grader doesn't know differential equation.
Then how do they know what d squared dx squared means?
Oh.
Does everybody in the universe know what that means?
That's
Do we
true.
have to reintroduce calculus too?
It's time to
Okay,
Unless
let's
you're
go.
ready to teach everything from kindergarten
Yeah.
level, you should come in with base presumptions
Okay,
of
all right.
what
So,
on
But,
Then-
but can you write it nicely, like partial t? It's not. Can we write it in a?
It's okay. Which
Raf,
looks nicer to
then it's okay. It's not for all fifth grade. It's not for all fifth graders.
Which looks nicer to you?
This one.
Shut up! I do not care about your opinion. Okay. There'd be no choice anyway.
This is a dictatorship.
Hell yeah, it is. You said it wasn't. And of course we have not c squared. We're gonna die.
No, right? How do you write it here? You actually write it this way?
Yeah, but okay then.
Yeah, the C's don't matter. They're just constants.
C. Or yeah, maybe we can just kill it all.
Okay, so what's the first equation you have there? Where's the E? Where's the energy?
Well, you told me to remove it because it was a constant.
No, keep the energy.
Die.
Okay. Well, what about F equals ma?
Okay. Well, that's just.
Okay. Now we can learn something. Now you wrote down the equation.
What's learning?
Now we can learn something about the solution. Okay? What does the solution to this equation look like?
Well, it's just going to be a linear.
Just a linear, right? What does that mean physically?
What that means physically is it's going to be traveling at the same rate through space.
Why?
Velocity is never going to
With the same acceleration.
Okay. The way I put it is just integrate with respect to time once.
Yeah, no, we know we can do the math.
Yeah.
Physically, what is it saying? Oh,
Physically, what it's saying is
that
that
you wrote down the 4 equations.
Oh, wow, very nice.
This is F equals, can you explain what this is?
Well, this is the equation for any particle in quantum mechanics.
That's Schrodinger's equation.
Electron. This one is the heat equation, this one is a wave equation, and this one is
F equals ma. So look how similar they all are. Look, what is this? Wave equation. Wave equation and F equals ma both have the same left-hand side.
That's what I was trying to say, but
But the Schrodinger equation and this share almost nothing in common.
No. Now, okay, let me explain. Let me show
They
you.
only look
Okay.
similar because we use
no, Isaac gonna yeah, you can rotate. Isaac, go to the other side.
Okay, so here's what we see. Okay, can I erase this, please?
No, you can do down so people have reference.
Okay, I need space.
Oh, okay. So then sit down because you're blocking.
Okay, I'm gonna.
Sit over there on the other side. Isaac,
No, I have to stand.
oh, stand up. Okay.
Yeah.
Then Isaac, put the chair over there and sit down. One of you have to sit down. Not like this.
Okay.
You have to look at the board.
Oh.
Not like this.
Do it sideways.
Can you do it the way you did?
Like this.
Okay, so what is the way you wrote F equals ma?
Partial x squared,
Yeah.
0 is equal to partial x squared psi.
Okay, very simple, right? This is if there is no force, right?
Mhm.
There is no force,
Mhm.
then there is no acceleration,
Mhm.
right?
Mhm.
What does that mean?
Well, that means the particle is just moving in a linear rate.
Yeah, that.
There's no acceleration.
Let's draw the dt, vt.
Oh my god.
No, it's our audience is fifth grader.
Yeah. So
Okay.
if acceleration is 0,
Mhm.
then a looks like this, v looks like this, d looks like this, right?
Yes.
So all this is saying is that particle is moving at constant velocity, but there's no acceleration
At positive direction.
in the positive direction. Yeah.
Oh yeah, these are just guesses, by the way. To actually know what it would look like, you'd have to.
Okay, good. Done, right?
Yes.
Now let's upgrade. Okay. We upgrade to the next thing, which is the wave equation. So the wave equation is, I'm going to write it right under it. So d squared, I'm going to put psi instead of x.
Oh, so we can, again, the F equals ma is similar to.
Yeah.
I'm just not seeing it, given that psi and x kind of act like totally different objects.
No, x is the position distribution.
Well,
But here there is no
Graph.
distribution.
there's no distribution
Because
from
it,
the
you,
mechanics.
exactly. So psi for Newtonian mechanics is the same thing as x.
So, I mean, what's what's the point?
The point is we're just trying to draw an analogy between, because I mean here if I kept it psi it would be confusing with this x, but psi here serves the same purpose as x.
Sure.
So what's the solution to the wave equation?
The solution to the wave equation is going to be in e to the I something.
Yeah.
I can't do it more in depth because I don't have.
Yeah, that's right. So the solution to the wave equation is just some kind of a wave, right?
Well, yeah, I could have actually solved it if
Yeah.
I had the time.
Exactly. Okay. Now, let's go to the third one. Okay. What's the next thing?
That's a heat equation where you move the from outside.
And what's the only thing different about the heat equation?
d psi dt instead of d squared psi dt.
What is the solution?
I don't remember, but don't you get suddenly a totally different solution?
Well, this is how the heat equation looks like. This is the solution.
And wait, here psi is starting to take on its meaning of a distribution.
Yeah.
Because
Because it's also a distribution here.
yeah, because now it's the heat distribution. Like not
Oh, are we? Oh, it's still rolling, right? No.
Yeah. You guys good.
Don't we need the light?
No, you don't. Light is distracting.
So the solution to the heat equation looks like this. You start off with, let's say you have a rod, right? Only one part of the rod is very hot in the beginning.
Yeah.
But then it
It smooths out.
exponentially decays over time. Right?
Yes.
This is the solution to the heat equation. And then finally,
I wouldn't label the y-axis as phi. I would label the purple line as phi.
yeah, that's what
Or
it's
psi.
it's supposed to represent. It's the heat distribution. Psi here is the heat distribution as a function of x and t. Okay, and then finally we write down the Schrodinger equation. So the Schrodinger equation looks like what? What is it?
It's just
Oh,
e
yeah.
psi.
D squared dx squared is E psi, right?
Yes.
Okay, so, and what does the solution to the Schrodinger equation look like? For a free particle?
Well, for a free particle, for a totally free particle, it's just going to be one. It's going to be a sinusoidal overall
It
space.
is going to be a Gaussian, right?
No.
Because when you add up the sinusoidal, if it was just a sinusoidal, that would not have a normalized probability distribution.
Hold on. What happens if you actually use the Gaussian? E to the minus x squared.
You have to integrate it.
No. Well, what happens when you actually plug it in here? Let's see if it's.
Oh, it's not going to be a direct solution of this, because the solution to this is a sinusoidal.
Yeah, that's what I just said.
But you have to add up sinusoidals of different frequencies so you can get a normalized distribution. So plugging this in here won't give you a solution.
So you're basically forming a Fourier series.
Yes, that's right. So this is just one of the many solutions,
Yes.
right? Because you just directly take this, it's not going to satisfy that the probability has to add to 1, right? So this is, this is one of the many solutions that
So you're looking for a convergent Fourier series to solve
yeah.
this.
Okay, but let's keep things simple. Wait, so the first thing here is f equals ma.
Mhm.
What is the solution to f equals ma?
It's linear.
If there is no acceleration, then dt looks like this. Okay, you just have an object moving to the right with a constant velocity. This is the wave equation, right? Look
An example would be Earth.
What?
for
Earth moving with constant velocity.
Earth is not moving with
well,
constant velocity.
We can ignore the little acceleration.
No, there's
Yeah.
a lot more.
Sure, yeah, I mean-
acceleration.
If
Yes.
Earth was not moving with constant velocity, why is initial reference frame?
Okay. Ooh, okay, fine. The acceleration is too small to notice.
Okay. Alright, so, okay, second one.
So this is the f equals ma. So notice that f equals ma has this dt squared, right? So this is the wave equation. It looks the exact same as f equals ma, but now on the other side there is a,
Yeah, that totally changes the characteristics of the solutions.
now the solution looks like a wave
Mhm.
for the wave equation.
I want example.
So
Isn't that an example?
an example of a solution to the wave equation is sine of x.
You have to
So-
include something in the t. There has to be a t
So
component.
sine of x minus omega t is an example of a solution.
Sure, that would
Or
be-
plus minus.
Yeah, sure. Depending on which way you want it to.
You probably actually solve it just by taking e to the ax plus bt and then
Okay, yeah.
doing the one to
Yeah, we know how to solve equations, right? But I just want to focus on the end.
Was that Gaussian?
No.
This one.
No, the other one. He wrote e to
to
the.
the ax plus bt, that's just an exponential, which turns into sinusoidal if a and b are imaginary. The thing is, a Gaussian
has an x squared.
minus x squared.
Okay.
X squared is a lot less interesting than minus x squared.
So this is Gaussian. This is exponential.
Okay.
Yeah.
Okay.
No, it doesn't matter.
Why are you being paid?
Sorry, okay, fine. Okay. Wait, what?
Wait, what?
Okay. So, okay, you explain the other two. Please.
Fine. Okay. So this is the heat equation, and what it's basically.
Baby Isaac.
Yeah.
Then you have to come here. Raf has to sit down.
Wait. So this term sort of acts like the flux, right? And all it's so the flux is basically just which direction the heat is going over time. So all it's doing is relating where the heat currently is to where it's going to spread out. And so if there's a spike of heat in some center, it's eventually going to spread out in accord to this equation. And finally, the fourth equation, d squared psi dx squared e psi, of course, independently, the simplest solutions are just sinusoidals, but those integrals diverge from minus infinity to infinity. So what you want instead is, this is actually a linear equation. So, if you rearrange it a little bit more, you can just put it as psi prime prime minus e psi is equal to 0. It's a linear second order homogeneous equation, which means that if one solution is A and one solution is B, then any linear combination of them is also going to be a solution. Which means that an infinite linear combination of them should also be some sort of solution, right? Which is why, with some Fourier series, you can get something like e to the minus x squared out of it. Yeah, that's probably not a perfect explanation. But
I think people won't understand this. I think it's a great, you know it, but I think it's overcomplicated.
okay, fine.
But can you tell people, just compare the solutions. Forget about the equations. What do these solutions mean? Can you just explain?
Well, they're all totally different from one another.
Yeah, so can you explain?
This is because there's no
Okay.
acceleration. That's literally what the equation says.
Okay.
This is sinusoidal because the acceleration essentially has to be proportional to the curviness. This, well, we're dealing with the distribution now, so we can't exactly classify it as a function of any sort. But essentially, it's just telling us that this distribution is going to spread out over time. And the same thing with this. This is just telling us, since we have no potential here and no time-dependent terms anyway, this is telling us that our distribution will be constant in time, so we can talk about it being some sort of function again. And in terms of what function it is, it can be pretty much anything written as writable as a Fourier series, but in this case we've drawn it as a Gaussian. But it could also look like a sinusoidal or, I don't know, a square wave, whatever you want it to be.
Nice, good job. Also, it can't be a sinusoidal. That's not normalizable, and it can't be a square wave.
I know.
Okay.
Those are not normalizable. I'm just saying they're solutions. Non-normalizable doesn't mean they don't exist. It just means they don't have physical meaning.
So they don't exist.
They don't exist in the real world.
So they don't exist, period.
But math is all about things that don't exist.
Oh, like relevance?
No.
All right. Now, 10. Now 30-second challenge. Raf, you're gonna challenge him based on what you have on the board. Go.
Any question?
Yeah. Any question?
Like challenge me in terms of math or just the conception?
No, this is quantum. Okay. Go.
Okay.
No, I mean challenge me in terms of a mathematical.
Yeah.
Based quantum.
Yeah. Go.
Okay.
Isaac, don't.
Let's see, I have many questions, but let's see. How is Schrodinger's equation similar or different from the heat equation, the wave equation, and F equals ma? Compare Schrodinger's equation in differential form to these three and its solution to these three, and explain why there's an uncertainty principle here, even though there's no uncertainty principle in the other equation that also has a second derivative in psi.
Okay, so let me remember where the uncertainty principle is derived from.
Do you want a hint?
So the uncertainty principle depends on the commutator.
I can give a hint. Think.
Oh yeah, it depends on expectation values and all of that funky stuff. Isn't it because here psi represents a probability distribution more than anything, and here, meanwhile, psi represents a heat distribution. Here, it doesn't even represent a distribution, and here it's just a point.
Yeah. So where does the uncertainty principle come from? It comes from
Probability.
birds.
What the fuck?
You try to take a picture of a bird. If the bird moves too fast, you don't know where it is.
In fact,
Buddy, do not try that analogy with me.
we took the picture in the morning. We took the picture in the morning.
Captured the uncertainty principle.
No,
Action.
no. It comes from probability. It comes from
Okay,
probability.
fine. I'll tell you the truth.
You wanna see the picture?
It comes from probability.
You wanna see the
It
picture?
comes from probability.
Okay.
I wanna show
It
you.
comes from probability.
Here is the
It comes
picture.
from the expected value.
How can you deny this picture?
It's just a dumb analogy.
How it is dumb?
Yes, it is.
We took it. What is the picture? Oh,
You're
here. Here is the picture.
This is an electron. It's not what it looks like. It's not a notebook. It's an electron.
We did it in the morning.
Yeah.
We worked hard behind the
This
scene.
was a single electron.
Daddy loves it. Daddy loves it.
Wait. Okay, fine. I'll tell you the truth. Okay. I was the one who invented the uncertainty principle.
Yeah, no.
Okay, fine. I went to Helgo.
Did you put on like a funny mustache and call yourself Heisenberg for it?
Heisenberg did not have masters.
Yes, he did.
He did not have masters.
And
He did
also-
not. Heisenberg was the most smart. Einstein. No. But Heisenberg did not have
Einstein
masters.
had a mustache.
That's
When you go to
No, but Heisenberg didn't have a mustache, but he also.
Oh no, Heisenberg did not have masters.
Yeah, I'm saying he didn't have a mustache, but he also didn't have skill.
No, you're supposed to do those things. No?
Okay, fine. I'll tell you the uncertainty principle actually comes from the Fourier transform.
But I saw it derived from probability.
That's another. Okay, so one way you can get it is from the commutation relations. Okay, because this. Let me write it. So this is the uncertainty principle, right? Do you know the other uncertainty principle?
Well, the generalized uncertainty principle.
Okay, write it.
So, if you have quantity 1, I don't
A,
know, let's
let's say
call it x1
A and B.
and x2, that has to be greater than or equal to the absolute value of 1 over 2 times the commutator of their operators squared. Sorry,
Yeah.
I can't write it very well.
Oh, that's pretty good. Now, what if?
Finish it in 10 seconds.
It's already too late?
Oh, okay. I think this is a good job.
All right.
I
So
think
summarize
that's a
it.
good
Rab
job.
summarize it, or Isaac summarize it.
It was cool. I liked it.
No, can you explain these 4 equations,
I already explained them.
but in a nice way?
What does that mean?
Move your hands and explain.
I did. Am I not moving my hands?
Pictures.
I did. What?
Find one mistake in this board. One hole.
Wait, what?
What? They're not always a mistake in everything.
Wait, okay.
F equal MA doesn't work sometime. For example, so there's
That's not a mistake. That's a shortcoming.
shortcoming.
Oh, fine. Oh, here's a question. If you have 2 conserved quantities, then what is the commutation between them?
If you have 2 conserved quantities, wouldn't it be 0? Wait, no. 2 conserved quantities, which means they stay the same over time.
Do you remember the relationship between commutator and the Heisenberg evolution equation?
No.
How does it not produce this time? So it's like d a hat, where a hat is some operator, is proportional to the commutation of a hat with the Hamiltonian.
Oh.
And if this is 0, then that means a commutes with the Hamiltonian and a is a conserved quantity. So yeah, you could use this to also get some more intuition about where the uncertainty principle comes from. Because both x and, actually, X doesn't show up in the Hamiltonian if there's no potential, but P definitely shows up. So if you just have a free particle Hamiltonian, P squared over 2m, then P commutes with P, right? So really, another way, P commutes with P, so dP dt is 0, so there's no force on the
Holy
particle.
hell.
So,
Yeah, that was interesting.
okay. You want to see the derivation?